So notice this car is going to collide with this car, right? This guy's moving at 0 meters per second, right? So here's the train carriage B, right? Okay, notice that its initial velocity is 0. So here's our graph, right? After the collision, notice that it's moving at 5 meters per second, right? Okay, we can read the graph, right? Okay, and then train car A is moving at 6 meters per second before the collision, and then after the collision, notice that train car A is moving at -1 meters per second. So let's draw a little before and after picture. Okay, so here is A and B. All right. Okay, so we've got 500 moving at 6 meters per second. And this guy's moving at 0 meters per second and is 700, right? And then afterwards, we've got this poor guy here is actually going this way at -1 meters per second, and there's 500, right? And then this train car B is moving this way at positive, what is it? +5, right? And this is 700, right? It always helps me to make a drawing like this, right? So I got these velocities of -1 I got from the graph, right? The +5 I got from the graph, because we're supposed to use the graph, right? And the fact that it's at rest, you can either read from the graph, that is train carriage B is going 0 to begin with, right? Or you can get it from here. It tells you that it's at rest and that this one's moving at 6, right? Okay, so deduce that the total momentum of the system is conserved. That means that this momentum equals that momentum, right? So you're going to go m times v for this guy plus m times v is 0, right? Because it's not moving, okay? Then the question is, does it equal? So calculate this, right? And then you can calculate this. Notice that this guy's moving backwards, so don't miss that minus sign there, right? And then this guy's moving forward, so that's positive, right? So this times this plus this times this, does that equal this times this, right? So that's what you're going to do for the momentum. Now we have 2 marks here, so maybe the first thing to do is to state if the momentum is conserved, then the momentum before equals the momentum after, right? So say something 2 and then show the calculation. Yes, the momentum before equals the momentum after, so therefore it's conserved, right? You never know what the 2 marks are for, right? Okay. Now we want to show that it's elastic, right? And then the hidden bit of knowledge here is that we're going to do the same thing with kinetic energy. The kinetic energy before, does it equal the kinetic energy after? If it does, then it's elastic. Okay. So we're going to do the same exact thing, only now we're going to look at energy, right? So we're going to go 1/2 mv squared for this guy, right? Okay. And then, of course, this guy's not moving, so it's going to have 0 kinetic energy. Does that equal 1/2 mv squared? Now, remember, it's v squared, so don't put the minus sign in there. Or if you insist on doing it, put it in parentheses, okay? Because your TI calculators will square a negative number and get a negative answer. So just be careful there, right? So this kinetic energy of this guy plus this kinetic energy of this guy. Remember, there's no such thing as negative kinetic energy, so these are going to be 2 positive terms. And you'll find out that indeed it is elastic, that this kinetic energy here is the same as this kinetic energy, right? Okay, so show your calculations, show it on the dotted lines, and you should be good.